All right, we're going to talk about inverse functions or inverse equations. We have two objectives today. We're going to look at using structure algebraically, and we're also going to create these inverse functions or equations. And we're going to do this in kind of a generic sense, and then we're going to use it in an applied sense. So the first thing I want to do is I want to start with a linear function. So we're going to start with something of the form f of x equals some slope term, the independent variable, and some y-intercept. And I want to find an inverse function. Well, what does an inverse function mean? An inverse function means that the output of this function can be put into the other function and get our initial value back. So to illustrate that, I'm going to make a table of values. So for this function here, let's make a table of values. And let's plug in some inputs. Let's do -1, 0, and 1. Those are all easy to calculate. If I plug -1 in here, I have 2 times -1 plus 3. So this is going to be -2 plus 3, which is equal to 1. And so we continue on with that. If I plug 0 into here, I'll have 2 times 0 plus 3. That'll give me 0 plus 3 is 3. And then if I plug 1 in here, I'll have 2 times 1 plus 3. So 2 times 1 is 2. I have 2 plus 3 is 5. So my table of values is this. So the input here was the x values and the output was the f of x values in this table. Now, if I have an inverse function, I should be able to take this second column, this output column, and put it into my inverse function and get out this first column. So I'm going to create this mirror table over here. So here is my mirror. Everything that was in the first column is in the second column over here. Everything that was in the second column here is in the first column here. Also, notice my notation. The f of x that I had here has this exponent of -1. That is the convention that we use for denoting that this is an inverse function. And so how do we get from here to find this mysterious function that has these properties? There are a few steps that we're going to go through to do this. All right, our steps are going to be that we're going to replace the function notation with a y. So this f of x is going to be switched to a y. Then we're going to swap the x's and the y's. So everywhere that we see an x, we're going to replace it with a y. Everywhere that we see a y, we replace it with an x. Then we are going to solve this new equation for y. And then finally, we are going to replace that y that we have in this new equation with the inverse function notation. So I'm going to run through with this example. So step 1 is replacing f of x with y. So I'm writing a y here. So I'm going to have y equals 2x plus 3. Then I'm going to swap x's and y's. So I have a y here. It's going to become an x. I have an x here. It's going to become a y. And so I have this new equation. And now I'm going to solve this for y. So this is our normal algebra skills. So I'm going to subtract a 3 from both sides. And then I'm going to divide everything by 2. And so I'll have 1/2 x minus 3/2 equals y. And I'm just going to flip those so that the y is on the left. And now I'm going to replace this y with the inverse notation. And so we have this function. And now we can test this function. We can take one of our former outputs from this and plug it into here. So just as a reminder, one of the inputs that we put in here, we did a -1. So we did 2 times -1 is going to be -2 plus 3 is 1. So we're going to plug 1 in for x here. And we should get back -1 if this is the inverse that we were looking for. So 1/2 times 1 minus 3/2. 1/2 times 1 is 1/2. So we have, this gives us, we're looking at 1/2 minus 3/2, which is going to give us -1, because we have -2/2, which is going to be -1. And so that is the original input. So this is acting like an inverse function, an inverse of this function that we started with. So you can check it point by point. And if you learn how to do compositions, then you can check the entire function all at once. All right, we're going to look at a practical application of inverse functions. We're going to start with this equation, and this is how you would go from Fahrenheit to Celsius. You plug in a Fahrenheit measurement of temperature, and it gives you a Celsius measurement. But if we wanted this to be the Fahrenheit equals some expression with C as the independent variable, we would solve this for F. This is the same as going through some of our steps that we had before. We removed the function notation. This wasn't written in function notation, so there's no function notation to remove. Then you switch your x's and your y's. Again, we don't have x's and y's in this. But what we end up doing is, if this was y, it would move into here, and we would solve this for y. So what we're really saying is we're going to take this equation and solve it for y, which in this case is playing the part of the independent variable. So that's what we're going to do. So we're going to solve this for y. So the first thing we're going to do is we're going to multiply both sides by the reciprocal of the fraction. And that's going to eliminate that fraction. It goes to 1. And 1 times this is going to be itself. So we've taken care of that. There's nothing to simplify in the parentheses. So the parentheses at this point essentially go away. So I'm going to add 32 to both sides. And that leaves F by itself. Now, by the symmetric property of equality, I'm going to flip this around. All right, so this is our equation. If we know a Celsius value, we can plug it into here and simplify this, and we will know what Fahrenheit is. So this is the inverse of what we started with, which was Fahrenheit was our independent variable that we were plugging in, simplifying to get Celsius. So this is practical application of the inverse. This is the inverse function or the inverse equation of what we started with. Again, I don't have this written in function notation, but you could easily do that. Cheerful calculations.